question number 7 of the PhilNITS FE afternoon portion of the exam. We are now in sub-question number 2. And in this question, we have to remember that we are working on a heap data structure. And a heap data structure is a binary tree, in this case, a complete binary tree. And to show us what it would look like as a binary tree, we have this figure here, and just below it I put here the array representation of the binary tree, and what we need to do is to sort it in ascending order in this case, and then from there be able to find out if the code has to be updated, has to be changed, or whatnot. But in this particular sub question, what we are being asked for the blank H is really if you got the unsorted scores in this way and the sorted scores in this way, what should be the correct answer in the blank? Okay, and I think when I was answering this, I thought that it shouldn't be too difficult because if you look at the example here, where if the scores are unsorted and the output after going through the program would be the sorted list, then we can see that if you see first 80, which is a score that appears in another student's score, then you put it first in this way, and then the second one, the next one that you see, you put it right after it, right? So I thought that that should be the hint already, and it shouldn't be too difficult to answer anymore, because it seems like if you see the score first, then you put the ID in front of the next one that has the same score, because the student, for example, can get the same score, and in this case it will be 80, right? So one student gets 80 and another student gets 80, and so it seemed to me that when you sort it, then you'll get the arrangement in this way. But turns out, if we look at the answer key, it's saying that the correct answer is supposed to be C, which means that even though we see 84 for ID 0, the student's ID 0 first, it doesn't necessarily mean that it would come first when we sort it, right? And that's why I needed to figure out why it's like that, and to do that I came up with this kind of like a map, really, of how things are supposed to be connected to each other. And you can see these parts in the description and the text, but you really have to arrange them in such a way that it's easier for you to see how things are and where things are going in a bird's eye point of view. Now in this case, if we look at this part of the function, the rank by score, we do have heap up and heap down, which are also functions that we are using to do the heap sort. Now, since I got the answer incorrect, I thought that, okay, it looks like I need to really try out all the steps, more or less, particularly step 1 and step 2, these two, to see what the explanation is to the answer key's answer. Now, if we're gonna do step 1 first, which is the part where you got the heap up, I have to take note that it's going from 0 to n, where n is not included, okay? So we're incrementally going that direction, while for step 2, it's the other way around. We start from n minus 1, and then until we get the number before 0, okay? And n should be the the total number of elements. In this case, it's not 10, but 1, 2, 3, 4. There would be 4 total elements because we had to change the input data for a previous number in this sub question. I think that should be the letter G. Now, if we look at the first step, we do have the heap up here, and then the function is this one. And we can see that if we are gonna put in the parameter which is the child starting from 0 until n minus 1, then we can gradually see how things are gonna move in terms of the position of the values. Okay, so for example, we are starting first with this one. This is the input, right? And then it's saying that if we look at the portion here of the code, that the parent would be computed using this equation. So our input would be the child, and you can compute the parent, the index of the parent, using this equation, okay? And I'm using that equation in this part of my explanation. And it says that if the child's value is greater than the parent's, then we have to go into this portion of the code and do a swap. Okay, this particular here, do a swap. So if we look at it in this way, we start off first with 0, and then we compute the parent's index. In this case, it's 0 minus 1 divided by 2. And we have to put a parenthesis here because we have to do the subtraction first. And that will give us 0. And so the condition here isn't met. So we don't do any swapping at all. And we move on to the next one, incrementally going one by one to the n minus 1. And the child in this case would be the index of 1, which would be this one in this case. And we need to know what the parent's index would be. We do a 1 minus 1, this one first, and then divide it, and we get 0. But the problem is we don't do a swapping because the child, in this case this one, and the parent this one, they're equal. So if the child's value is not greater than the parent's value, then we don't do any swapping at all. Now for the second one, starting from 0, the child's values, the child's index I mean is 2, and the parent's index would be 2 minus 1 divided by 2, which gives us 0. And so when we look at the inputs, we got 2 here for the child, okay, and the parent here is here at 0, index 0, and then the value. What do we see? The child's value 96 is greater than the value of the parents, which is 84. Remember this condition here, this one here. So that's why we need to do a swap. And when we do a swap, number 2 here, the ID of the student will be here next, and then the ID 0, the student with the ID 0 would be here. Okay. Now if we move on to the next, because remember we have 4 elements and we're starting from 0, and so 4 minus 1 is 3, so we still have to do this one. And if we look at the parent's index based on the equation, 3 minus 1 divided by 2 gives us 1, and so that would be For the child first, we have this one, and the parent would be this with this one. Okay. So what that means is that they're the same. The value 84 is the same. We don't do any swapping at all. Okay. So we end up with this one for the first step. Now we need to do the second step, which entails doing a heap down. For this step, usually we look at the heap down function and forget that there's swap and heap size here in the inside of the for loop as well. And remember too that the for loop tells us that we start our counting from n minus 1. And n is supposedly the number of elements in our data, input data. For example, if it's 10, then n minus 1 gives us 9. And we gradually go down until we reach the number before 0, which is 1. But in this case, for this sub question, we change the input. The count is now 4 instead of 10. So the elements, the number of elements is now 4 instead of 10. And then we do a swapping from the first element to the current index, the first element and the element for our current index, and then we do a heap size minus minus, and then that's when we go to the heap down function. Okay, so it's important to keep that in mind. And so if we look at how things are with our data right now, the positions are in this way, and remember we have to do a swap first, the first element and the current element from our counting. So it's this one and this one. We swap them together. So we get the 3 here instead of there, and then the 2 is now here. Okay. And then that's when we go into the heap down function. This one. Okay. And in this case, the input would be the parent, and the left child, for example, will be computed as parent times 2 plus 1. And we have it here as well, except that this portion won't be too much of a necessity in our case. And so we'll still do them, but really the swapping will be more of the portion in the code before we get into the heap down function. Okay, so just to see what will happen if we get into the heap down function, the parent would be at 3, and if you compute the left child, it would be 3 times 2 plus 1, which is 7. And we know that the heap size is, because we had to do a heap size minus 1, it should be from 4 minus to 3, because we have to do a 4 minus 1. So the heap size would now be actually 3. And we know that because the left child, is already beyond the heap size, then we don't do any of these stuff anymore. Okay, we're focusing on the left child because the default is left child. Okay, in this portion of the code, and saying that if it's only when the left child is less than the heap size that we get into this portion of the code here. But because the heap size is also going down and the left child is currently at 7, we don't need to do any of this stuff. Okay, even though we also have a swap here and heap down here, we don't need to worry about that because we don't get into the function like heap down and swapping, just because we have an if statement here saying that it's only when the left child is less than the heap size. Okay, now if we incrementally go down some more, because remember from our if statement, where you got the swap, heap size, and heap down, we have to incrementally also go down. And remember too that we have to do a swap, and that's why because this one and this one should be swapped, and that's why we get the output here like this. Okay, so 3 would be moved here and 0 would be moved here. Okay, and the other thing here is that because we're doing heap size minus minus, we don't move this part anymore, the last part. That's why I also have this line here saying that we're um, removing the parts that are already sorted. Okay, now once we've done that, we've swapped those things, and we've also reduced the heap size so that it will be this one and this one. Now we can get into the heap down function, and we can see that if our current number is 2 and the child is computed as 2 times 2 plus 1 is equal to 5, and we again have this minus 1, so that this one is now 2, then it's again beyond the heap size. The left child is again more than the heap size, so that we don't get into this function again at all. Okay, now again we go into the increment going down, and what we have would be we swap this one with this one. Okay, and that's why the ID with the 1 would be here. Okay, and then of course the heap down function. Before the heap down function, we have the heap size minus minus. So this part here, they're okay, they're already sorted. And in this case, if we go to the heap down function again, and we have 1 as the parent's index, 1 times 2 plus 1 gives us 3. And in this case, continuing on with the counting here, this one would be giving us 1. And again, it's beyond the heap size. The left child is again more than the heap size. So we don't do any of these stuff anymore. Okay? And also, remember that we are only doing until the number before 0, which is 1. So that once we reach that number, then the next one will be 0. So we don't do this stuff anymore because we're done. Okay, it's only until before 0. That's why what we'll get is this set well in this position, and that's what we find for the answer C, so that the scores are now sorted in this way. Okay.